All right, diving straight in today. We've got a paper all about world models, and it's a real humdinger. This one's called Aether, and it's doing something pretty remarkable with synthetic data.
Yeah, this is some really cutting-edge stuff. Aether, short for Geometric Aware Unified World Modeling, is all about getting AI to understand the world in 3D, how things look, how they move, and how they change over time.
And what's super cool is that they're doing this entirely with data that's generated by a computer, not captured from the real world.
Right, and that's a big deal because collecting and labeling real-world data for 3D understanding, it's incredibly time-consuming and expensive.
Absolutely. So this Aether model, even though it's trained on this synthetic data, it's showing it can actually handle real-world stuff right out of the box. We're talking 4D reconstruction, like building a 3D model of a scene and how it evolves over time.
And it can do action-conditioned prediction, meaning you can tell it, hey, imagine this camera moves this way, and it can predict how the scene will change.
It's even able to do some basic visual planning, like, I want the robot to be able to see this object over here. What actions should it take?
And all of this, keep in mind, is on par with, or even better than, models that are specifically trained for each of those individual tasks, but using real-world data.
Yeah, that's pretty mind-blowing. So for anyone out there working with world models, video generation, or anything that involves getting AI to reason about 3D space and how it changes over time,
This paper is definitely worth a deep dive. They've got a project website too, ether-world.github.io.
Okay, so let's break down how Aether is actually doing this. It seems like the central challenge here is this whole problem of getting AI to have a human-like understanding of space. And that involves bringing together geometric reconstruction, which is all about building that 3D understanding.
And generative modeling, which is being able to create new visual data that looks realistic.
Right, so how does Aether kind of bridge that gap?
Well, it tackles this by combining three really powerful abilities into a single model. You've got 4D dynamic reconstruction. It's not just about seeing a 3D scene. It's about understanding how the geometry of that scene is changing over time. Think of it as the model building a kind of mental model of a 4D world.
Then you've got action-conditioned video prediction. So you can tell it, okay, imagine this action happens in this environment. And it can predict how the scene will change as a result.
And then you've got goal-conditioned visual planning. This is where the AI can actually figure out what actions need to be taken to reach a specific visual goal.
And what's really clever is how Aether learns these things together. They call it task interleaved feature learning. Basically, they train the model on all three of these objectives simultaneously.
Exactly, and this lets the different tasks kind of reinforce each other. What the model learns about reconstructing a scene helps it to predict how that scene might change, and what it learns about prediction helps it to plan more effectively. It's a nice synergistic loop.
Really clever. Now, I know some folks will be curious about the foundation of this model. What kind of video generation technology is Aether built on?
They're leveraging Cogvideo X5B I2V, which is a really powerful video generation model. But they're not just using it off the shelf, they're fine-tuning it using a massive amount of synthetic 4D data.
So all of this learning, this incredible performance, it's happening without the model ever seeing a single piece of real-world data during its training phase.
Right, which is, just incredible. That's what we call zero-shot generalization. It can handle real-world stuff, even though it's never seen it before.
That's a big deal. Okay, so Aether is trained on this synthetic data, but it also needs to understand actions, right? How is that represented in the model?
They're using camera pose trajectories as their way of encoding actions. It's basically a description of how a camera moves through space over time.
And why is that representation particularly useful for tasks like navigation or robotic manipulation?
Well, think about it. If you have a robot moving through a room, the path that its camera takes, that's basically its action, right?
Makes sense.
And in robotics, if you've got a camera mounted on a robot arm, the way that camera moves that directly captures the motion of the robot's hand. So it's a very intuitive and effective way to represent actions in those kinds of scenarios.
Okay, so we've got the synthetic data and we've got the actions, but how do they actually create this 4D synthetic data? That sounds like a huge challenge in itself.
Yeah, it's a pretty sophisticated pipeline. They call it their 4D synthetic data annotation pipeline. And it all starts with dynamic masking.
Dynamic masking, what's that all about?
So they're using this to figure out which parts of a scene are moving and which parts are static. They do this by identifying semantic categories like cars and people. These are things that are typically going to be moving in a scene.
Makes sense.
And they use a technique called grounded SAM2 to make sure that these masks stay consistent over time.
So if a car is moving from one frame to the next, it's still identified as the same moving object.
Exactly. They do acknowledge that this approach might sometimes misclassify things. Like a parked car might get flagged as moving, but it's generally more robust than using optical flow, which can be really noisy.
Right, optical flow can get confused pretty easily, especially if there's a lot of motion in the scene.
Yeah. So once they've identified the dynamic parts in the scene, they move on to video slicing.
Okay, so what's happening in the video slicing stage?
It's essentially a data cleaning process. They want to get rid of video segments that might mess up the 3D reconstruction. Things like sudden scene cuts or frames with a lot of motion blur.
So they're making sure the data is clean and ready for the 3D analysis.
Precisely. And they also break down longer videos into shorter, more manageable chunks. They've got some specific criteria for doing this, like if a segment doesn't have enough distinctive features, it might get tossed out because it's likely low texture or poorly lit.
So those segments might not be reliable for 3D reconstruction.
Right. Or if there's too much motion, or the optical flow is giving really wonky results, those segments get cut too.
Okay, so they've cleaned up the video and they've got these nice manageable chunks. What happens next?
Next comes coarse camera estimation. For each of these video slices, they use a tool called Droid Calip. It leverages the depth information from the static parts of the scene to make an initial guess about the camera's parameters, like its position, its orientation, and its internal properties like focal length.
Right, but you're calling it coarse. That suggests it's not super precise yet.
Exactly. It's a good starting point, but it needs some refinement. And that's where the final stage comes in. Camera refinement.
So how do they refine the camera estimates to get that high quality 4D data?
This is where they pull out the big guns.
Yeah.
They use CoTracker 3, which is a very sophisticated visual tracker. It finds these really precise correspondences between features in the static parts of the scene and tracks them over time.
So it's identifying specific points and following them across the entire video clip.
Yeah. And because they have access to really good depth information in this synthetic data, they can use something called forward-backward reprojection. This helps them to minimize errors in the 3D reconstruction, which leads to much more accurate camera poses.
And they're using something called bundle adjustment in this process, right?
Right. Bundle adjustment is a classic technique in computer vision. It optimizes the camera poses and the 3D positions of all those tracked points simultaneously.
Right.
They use the series solver for that and a Cauchy loss function to make it more robust.
Cool. So we've got the dynamic masking, the video slicing, the coarse camera estimation, and finally, the camera refinement. That's a lot of steps.
Yeah, it's a pretty involved pipeline, but the results speak for themselves. Figure 2 in the paper shows some really great visualizations of this annotated 4D data. It's really impressive.
It sounds like a really robust way to get that accurate 4D information from the synthetic video. Okay, so they've got all this beautiful synthetic data. How does Aether actually use this to learn and become a multitask world model?
Here's where things get really elegant. They take their pre-trained video generation model, CogVideoX, and they train it by randomly mixing up different combinations of inputs and outputs.
So they're not explicitly training it for each task separately.
Nope, it's all mixed together. They might give it a full video and ask it to reconstruct the 3D scene, or they might give it an initial observation and an action and ask it to predict what happens next, or they might give it an initial and a goal image and ask it to plan a path.
Wow, that's really cool. So the model is learning to do all of these different things at the same time.
Exactly, and that's what helps it to develop this unified, flexible representation of the world. It's not just learning isolated skills, it's learning how these different aspects of understanding the world are connected.
So let's talk about the specifics of how they handle the input data. How are depth videos processed before being fed into the model?
They do some pre-processing to get the depth information into a format that the model can work with. First, they clip the depth values to make sure they're within a reasonable range.
So no crazy outliers.
Exactly. Then they transform the depth values into disparity. Disparity is kind of the inverse of depth. It has a more linear relationship with distance, which is easier for the model to learn.
Got it. And I imagine they do some normalization to make sure the values are consistent across different videos.
Right. They use scale invariant normalization to prevent the model from being biased by the absolute scale of the scene.
Makes sense. What else?
After normalization, they map those disparity values to a specific range, usually between Moga 1 and 1. And because they're using a video VAE, they have to replicate that single channel disparity map across all 3 color channels.
Ah, right, because the VAE is expecting a 3-channel input.
Exactly.
Okay, so that's how they handled the depth videos. What about the camera trajectories? You mentioned they're converted into Raymap videos. How does that work?
Yeah, the Ring-Up videos are how they encode the camera's position and orientation over time. It's kind of like a map of where the camera is looking.
Okay, that makes sense. So how do they actually build these Raymaps?
Well, they start with the camera's intrinsic and extrinsic matrices. These matrices describe the camera's internal properties, like its focal length and its position and orientation in the world.
Right, those are the basic parameters that define how a camera sees the world.
Exactly. And they use those matrices to calculate the direction of the ray that goes through each pixel in the image.
So for each pixel, you know where the camera is and you know the direction the camera is looking, so you can trace a ray out into the world.
Precisely. And they store that information in these 6-channel ray maps. 3 channels for the ray direction and 3 channels for the ray origin.
Okay, so that's how they encode the camera's viewpoint. But I imagine they have to do some downsampling to make these ray maps match the resolution of the video data.
Right. They downsample the ray maps spatially to match the feature map size of the video model. They also do some temporal downsampling by concatenating every 4 consecutive frames.
So they're essentially compressing the ray map information in both space and time.
Exactly. And if you're interested in the specifics of how they convert those ray maps back into camera matrices, they've got a nice algorithm outlined in the supplementary material.
Okay, we'll have to check that out. So they've pre-processed the depth videos and the camera trajectories. Now let's talk about the actual training process. How do they train the Aether model using all this data?
Well, they start by initializing the model with the weights from the pre-trained CogVideoX model. But the layers that are specific to handling the depth and ray map information, those are initialized from scratch.
Makes sense. They want to leverage the existing knowledge from CogVideoX, but they also need to give the model the flexibility to learn these new tasks.
Exactly. And they're not using any text prompts in this work, so they just use an empty text embedding during training.
So it's purely visual learning.
Right. And to handle the fact that their synthetic videos have different lengths and frame rates, they randomly sample these parameters during training.
So the model is seeing a variety of different temporal scales, which probably helps it to generalize better.
Yeah, absolutely. And then there's this really clever trick they use to get the model to learn all these different tasks simultaneously. They randomly mask different input modalities during training.
Oh, interesting. So sometimes the model will get the full input, but sometimes it'll be missing some information.
Exactly. Like they might mask out parts of the color video or the entire camera trajectory. This forces the model to learn to infer the missing information from the context.
That's a really neat way to encourage the model to learn a more general representation of the world. It can't just rely on having all the information handed to it. It has to learn to figure things out on its own.
Exactly.
Okay, so what about the actual loss function they use to train the model? How do they measure how well it's doing?
The training happens in 2 stages. The first stage uses the standard loss function for latent diffusion models. It's all about minimizing the difference between the predicted and the actual latent representations.
So it's trying to make the model's internal representation of the world match the ground truth as closely as possible.
Right. And then in the second stage, they refine the generated outputs by adding some additional loss terms that operate in image space.
So they're not just concerned with the latent representation, they also want to make sure the model is producing high-quality outputs that look good and are geometrically accurate.
Exactly. They use different loss functions for the different output modalities. They got one for the color video, one for the depth video, and one for the 3D point clouds that they project from the depth and ray maps.
Okay, so they're really going all out to make sure the model is learning to produce high-quality results. And how do they manage the computational side of things? Training a model like this must require a ton of resources.
Oh yeah, it's a big model and a lot of data. They used 80 A100 GPUs for training, and it took about 2 weeks.
Wow, that's a serious compute cluster. Okay, so the Aether model is trained. Now let's see how it actually performs. Let's start with the 4D reconstruction results.
All right, so remember, all of this is zero shot. They're testing the model on real-world data that it's never seen before. And for reconstruction, they're focusing on video depth estimation and camera pose estimation.
Let's start with the depth estimation. How well does Aether do?
It does surprisingly well, especially considering it's never seen real-world depth data. They tested it on a bunch of different data sets, Sintel, Kitty, Bon, and it consistently performs either on par with or better than the state-of-the-art methods, most of which are trained on real-world data.
That's really impressive. And what about camera pose estimation?
It also does quite well on that. Again, they tested it on a variety of datasets, and it achieved comparable performance to models that are specifically designed for camera pose estimation. They did have to use a Kalman filter to smooth out the trajectories a bit, but the overall results are very promising.
So even though the model was never explicitly trained on real-world data, it's able to generalize and perform these tasks remarkably well.
Right, and that's really the exciting thing about this work. It shows the potential of synthetic data for training these kinds of models.
Okay, let's move on to the generation and planning tasks. How did Aether do on video prediction?
They tested this in two scenarios: action-free and action-conditioned prediction. For action-free, they just give the model an initial observation and ask it to predict what happens next. For action-conditioned, they give it an initial observation and a camera trajectory, and it has to predict how the scene will change as the camera moves.
And how did it compare to their baseline, which was CogVideoX?
Aether consistently outperformed CogVideoX on both tasks. Interestingly, they found that CogVideoX tended to produce more aesthetically pleasing videos, but they were often static. Aether, on the other hand, generated more dynamic videos that accurately reflected the provided actions.
So it's not just about producing pretty pictures, it's about actually understanding the dynamics of the scene and how actions affect those dynamics.
Exactly. And that's where the power of their approach really shines. They're not just relying on visual similarity, they're incorporating geometric understanding into the model.
Okay, and what about visual planning? How did they test that?
They looked at two scenarios: action-conditioned navigation and action-free visual path planning. In both cases, the model has to figure out a sequence of actions that will take it from an initial state to a goal state.
So it has to do some kind of planning in its head to figure out how to achieve the goal.
Right. And they found that the ability to reconstruct the 3D scene was really critical for doing this well. They compared Aether to a version of the model that didn't have the depth reconstruction objective, and the full Aether model significantly outperformed it.
So that 3D understanding is not just helpful for reconstructing the scene, it's also crucial for planning actions within that scene.
Precisely. It gives the model a much richer understanding of the world and how things are related to each other.
Makes sense. Now, every good research paper acknowledges its limitations. What are some of the limitations that the authors pointed out?
Well, they acknowledge that their camera pose estimation, while good, isn't quite as good as some of the specialized models that are out there. They think this might be because the way they represent the camera poses with these Raymap videos might not be perfectly compatible with the way the video diffusion model learns.
So there might be some room for improvement in how they encode that geometric information.
Right. They also found that the model didn't perform quite as well on indoor scenes compared to outdoor scenes. They think this might be because their training data was biased towards outdoor environments.
So more diverse training data could potentially improve performance in those more challenging indoor scenarios.
Yeah. And finally, they found that in really complex and dynamic scenes, the video predictions could sometimes be a bit off, especially when they weren't using any language prompts.
So incorporating language into the model might help it to handle those more challenging situations.
Exactly.
Okay, so some limitations, but also a lot of really exciting results. What are some of the future directions that the authors suggest?
Well, they want to explore different ways of representing actions. They think that going beyond camera trajectories might lead to even more control and flexibility. They also want to experiment with incorporating a bit of real-world data into the training process.
Yeah, even a small amount of real-world data might help the model to bridge the gap between the synthetic world and the real world.
Right. And they want to explore ways of bringing back the language capabilities of the base CogVideoX model. They think that could be really helpful for handling complex scenarios.
So overall, it sounds like Aether is a really significant step forward in world modeling.
It really is. It's showing the potential of synthetic data for training these kinds of models, and it's achieving some really impressive results across a range of tasks.
So for our listeners, what's the big takeaway here?
I think the big takeaway is that Aether offers a really powerful and promising new approach to building world models. It's leveraging the scalability and controllability of synthetic data to achieve impressive real-world performance across these really crucial AI tasks. And that could have significant implications for all sorts of fields, from robotics to autonomous navigation to video generation.
Absolutely. And it opens up a lot of really interesting questions for future research, like what other kinds of geometric representations could we use to encode actions? How can we make synthetic data even more realistic and useful for training these kinds of models?
We encourage everyone to dive into the paper and the project website to explore these questions further. There's a lot of potential here for really pushing the boundaries of what's possible with AI and spatial intelligence.
Absolutely. Well, on that note, thanks for joining us for another deep dive. We'll see you next time.